All right, so this is the second part of the lesson applying or looking at trigonometric ratios in terms of angles and standard position. And the focus of this lesson will end with us solving trigonometric equations, which we'll get to shortly. But first, again, I have a fairly standard sort of setup. I give you a point, and I say it lies on the terminal arm of angle theta in standard position. Sketch the angle and determine the exact trigonometric ratios for sine, cosine, and tangent. Okay, so again, the hardest part of this probably is understanding the abstract nature of what's being described here. This is describing an angle in standard position, as it says. So it always starts here and ends somewhere else, but it ends going through the point, -8, 15. So -8, 15 is in the second quadrant, so 8 over 15 up. I don't know, how about here? And so I know the terminal arm goes through here. So already the question is less abstract, and we can probably think of theta being like that. Okay, although again, that's not the only way theta, that's not the only way that the angle could end in that point. That's not the only possible angle for theta. That's it. I've sketched the angle, so let's determine the exact trigonometric ratios for sine, cosine, and tangent. Well, remember again, sine, in terms of an angle in standard position, the sine of any angle is a y-coordinate on the terminal arm divided by r. Cosine of theta is an x-coordinate divided by r, and the tangent of theta is a y-coordinate divided by an x-coordinate. Of all these three, only tangent can we actually figure out right away, because I know x and y. But for sine and cosine, I need to figure out r before I can figure those out. That's it, tangent. The x-coordinate is -8, the y-coordinate is 15, so I know the tangent of this angle must be the same as 15 divided by -8, or just -15 over 8. It's all the same thing. All right, so there's tangent. Sine and cosine, I can find out really quickly what the exact values of sine and cosine are for this angle, but first I need to figure out r. And again, r is the hypotenuse, essentially, of a triangle, should I draw one, or it is the distance. I've just highlighted in green. And remember, we can always figure that out from remembering that x squared plus y squared always equals r squared. Again, this is all really just review of last day. So in this case, I have -8 squared plus 15 squared equals r squared. And -8 squared plus 15 squared is 289, which actually is a perfect square. If you square it 289, you get exactly 17. Now I will say, thinking back to our quadratics units, anytime you solve something algebraically from here to here, there's a plus or minus possibility. However, r is a distance, it is the radius, or you can think of it as a hypotenuse. Either way, it's a distance, and distances are always positive, so I don't need to worry about that. There we go. So now I can find the exact values of sine and cosine. Sine must be 15 over 17. Notice sine is a positive number, which we would expect that when we're looking at an angle in the second quadrant, whereas cosine is going to be a negative number. It's -8 over 17. Which again, we expect cosine to be negative in the second quadrant. So keep in mind, I haven't figured out theta. In fact, I'm not going to. I'm not asked to. I don't know what theta is. I don't know what that angle is, but I know the sine of theta. I know the cosine of theta. I know the tangent of theta. All right. So determine the exact value of the sine of 210 degrees. Now, when I say exact value, I mean if you went to your calculator, there's a good chance it would give you a decimal approximation. And again, yeah, as we've seen for most of these last few lessons, we don't need a calculator. So what does 210 degrees mean in terms of an angle in standard position? In terms of a triangle, it doesn't make sense. You can't have a triangle with a 210 degree angle in it, but you can have a rotation. And 210 degrees in standard position looks something like this. Because from here to here is 180. Plus an extra 30 degrees. And so that 30 degrees there is my reference angle. Okay, that's it. All I've done is kind of draw what 210 degrees looks like in standard position. But what's the exact value of the sine of 210? Well, one thing I know about the exact value of the sine of 210 degrees, I now know it's going to be a negative number. Because in this quadrant, only tangent is positive. And I know that from the last lesson, that all trigonometric functions are positive in this quadrant, only sine is positive here, only tangent is positive here, only cosine is positive here. So I know the sine of 210 degrees is going to be the exact same, it's going to be a negative number. Now negative what though? Well, for this I just need to focus on my reference angle. And if I kind of zoom in on this, I can imagine a little right triangle here. And where I have a 30-degree angle there, and it goes through some point right here. Well, if I want to figure out the exact value of 210 degrees, I just need to figure out the y-coordinate and the radius. So if I can figure out a point on this terminal arm, then I can figure out the distance from here to here, and then I can figure out the exact value of the sine of 210 degrees. Well, how can I figure that out? Well, a 30-degree angle right there, if there's 30 degrees there and I have a right angle, then this must be 60, which means I can use one of our special triangles if I imagine, looking at this sort of triangle I'm drawing right here. And so for this particular special triangle, if the shortest side is 1, the longest side is 2, and the side in between is root 3, which means in terms of coordinates, the coordinates of this point right here, the x-coordinate must be -1. Sorry, got my x and y's mixed up. The x-coordinate must be negative root 3, because I'm to the left of the y-axis. The y-coordinate must be -1, because I'm down, and the radius must be 2. And so if I want to figure out the exact value of the sine of 210, all I need to do is find my y-coordinate and divide by my r. So I can see it's -1/2. So I knew it was going to be negative, but now I know it's -1/2. That said, this all came down to using my special triangle. What's even faster is realizing that that 1/2 I got right here, it's not a coincidence. That's the exact same as the sine of 30 degrees. Once we knew our reference angle was 30 degrees, really we could just start thinking about what is the sine of 30 degrees. And from that, we could just go directly back to our special triangle. So like I said, to accomplish this even faster, once I knew sine was negative, and once I knew my reference angle was 30 degrees, I could just think about a 30, 60, 90 triangle. And again, 1 to root 3. And then realizing, okay, sine of 30 is 1/2. And that's not a coincidence. I got 1/2 right there. However, in the end, multiple approaches to get to this -1/2. So the sine of 210 degrees is -1/2. Okay, what about this? And again, the hard part about all of this is not the calculations. It's how abstract this is. Suppose theta is an angle in standard position with a terminal arm in quadrant 3 and the sine of theta equaling -3/4. What are the exact values of cosine and tangent? Okay, so again, what does this mean? Well, let's start by visualizing what we can. We have an angle in standard position. I have a terminal arm in quadrant 3. So my terminal arm is somewhere in here. I'll just draw a terminal arm in quadrant 3. Okay, but I don't know a point that it goes through. And I don't know theta. Again, I can think of theta being like this, but doesn't tell us what it is. I do know the sine of theta is -3/4. So that does tell me something. Because the sine of theta is always the same as y/r, and I know it equals -3/4. And as well, I know the -3 I can think of as a y-coordinate, because radius has to be positive. Because if you think about it like this, if you think of it as 3 divided by -4, which mathematically is equivalent, -3 divided by 4 is the same as +3 divided by -4. But if we think about it like this, we're thinking about our radius being a negative value. That doesn't make sense. So that's how I know the negative has to apply to the y, to the numerator, the y-coordinate. Which means I know this terminal arm goes through a point, something, comma -3. And I don't know x. But I do know r. It's 4. Again, sine y/r. And so suddenly, this question is getting less and less abstract. And so if I want to figure out the exact values of cosine and tangent, I need to figure out this x value first. And now I can start to piece this together quite nicely, because again, I can use the Pythagorean theorem or this equation x squared plus y squared equals r squared to figure out x, because I know y and r. And so in this case, I'm going to say x squared plus negative 3 squared equals 4 squared. And so solve this quite quickly. I get x squared plus 9 equals 16. Subtract 9 from both sides. X squared equals 7. Square root both sides. I get x equals plus or minus the square root of 7. Notice right here I'm solving a quadratic equation. And in this case, I do want a plus or minus because x, again, is a coordinate. Coordinates can definitely be negative. So suddenly I have two possibilities for my x coordinate, either plus root 7 or minus root 7. However, if I look back at my diagram, notice where it is. X is in the third quadrant. X must be negative. So I know that my x coordinate must actually just be negative root 7 because I know I'm in quadrant 3. That's what it says in the question. And so now I can finish off the question. Now I can find the cosine of theta. The cosine of theta is always the same as x over r, which I now know x is minus root 7, and r I knew was 4 a while ago. Notice cosine is negative in the third quadrant. And tangent is y over x, which, again, y I knew was negative 3 a while ago. X I just figured out was minus root 7. And so a negative divided by negative, I really should write this as 3 over root 7. All right. And before I go on, I guess I should say that for tangent, 3 over root 7 is technically not in lowest terms. If you think back to our radicals unit, a rational expression is never in lowest terms if you have a radical in the denominator, but I don't care. I mean, again, this is not in lowest terms, but that's OK. I never said it had to be in lowest terms. OK. Come on, here we go. And this leads us to the final part and the most important part, which is solving a trigonometric equation. And that's what I have here. I have two equations, and I have an unknown. I have theta being my unknown. And again, theta is just a variable, usually to represent an angle. It's no different than if there was an x there. But what is x? So, and for each of these, I want angles, I want between 0 and 360 degrees. But first, let's just focus on this. So, I need to figure out where does sine equal a half? Well, I will say from memory, or from our special triangles, where the sine of what equals a half. Hopefully we can figure that out from memory, or again from special triangles. If you remember your 30, 60, 90 special triangle, 30, 60, 90, 1, 2, root 3, I can just look at this and realize, OK, where does sine equal a half? Well, the sine of 30 degrees must be a half, because from 30 degrees we have opposite over hypotenuse, 1 divided by 2. And so I know 30 degrees must be one possibility, because the sine of 30 degrees equals a half. So one of my answers is 30 degrees, but it's not my only answer. So how is it not my only answer? Because if I think about an angle in center position, sine, well, let me think about 30 degrees. 30 degrees looks like this, let's say. Here's 30 degrees. And the sine of 30 does indeed equal 1/2. But sine will also equal sine will also equal a half over here in the second quadrant. Because again, if I think about my cast rule, sine is positive in the second quadrant as well, which means sine will equal positive 1/2 somewhere in the second quadrant. And the position in the second quadrant will be the kind of a reflection of what it is in the first quadrant. And so if I know that this reference angle is 30 degrees, I know this angle is 30 degrees. Which means now I can quickly figure out this possible angle right here. And that angle from there that I drew in green is 150 degrees. And so going back to the actual question, the sine of theta equals 1/2. So what is theta? Theta equals 30 degrees or 150 degrees. There's two solutions to this equation. And if you go to your calculator and you type in the sine of 30, it will tell you 0.5 or a half. And if you type in the sine of 150, it'll tell you 0.5. That just kind of confirms that we're correct. Again, we're trying to solve these equations so we know what it equals. We're trying to find the angle that equals that. And in the end, it connected back to our special triangles, our cast rule, our angles in center position. connects back to a lot of little things. All right, so let's look at this one. The cosine of theta equals negative root 3 over 2. Well, first let's think about the cosine of what equals positive root 3 over 2. Because again, root 3 over 2 should sound familiar. And again, it comes back from our special angle. In fact, from this same one here. I can see if I look back at this special triangle right here, that if I look at 30 degrees, in fact, cosine is adjacent over hypotenuse, root 3 over 2. So I know that the cosine of 30 degrees is root 3 over 2. However, I'm trying to find out where does cosine equal negative root 3 over 2. So again, this 30 degrees here is very, very important, but it's not one of my answers. Because again, I'm trying to find where does cosine equal negative root 3 over 2. However, that 30 degrees is my reference angle. So important. Just like in the last question, the reference angle was also 30 degrees. And once I found that, my calculations were quite quick. But again, because I'm trying to find where cosine equals negative root 3 over 2, 30 degrees itself is not one of my answers. That's it. Let's go back to an angle center position. Let's think about where is cosine negative. Because now all that's left is I know the reference angle. In which quadrants is cosine negative? Cosine is negative in the second quadrant and the third quadrant. And again, I know the reference angle is 30 degrees. And so since I want answers between 0 and 360, I can now see my two solutions. One of my solutions is right there, which is 150 degrees. And my other solution is right here, which is 210 degrees. And so those are my two answers. Theta equals 150 degrees and 210 degrees. And again, if you look at my work, that 30 degree special angle, or that 30 degree reference angle, really, really important, although in this case it wasn't one of my answers. Because again, the cosine of 30 equals positive root 3 over 2. We're trying to find where cosine equals negative root 3 over 2. All right. I believe these are the last two questions for the final problem. Oh, these are just the last two problems. All right. So for these, we will actually need a calculator at some point. How do I know that? Well, first, for the tangent, where is tangent equal negative 1/2? Let's first think about where tangent is negative. Going back to our cast rule, tangent is negative in the somewhere in the second quadrant and somewhere in the fourth quadrant. Okay, and wherever those are, they have the same reference angle. So whatever that reference angle is the same thing as that reference angle. But what's the reference angle? Well, to figure out the reference angle, I now need to focus on the 1/2. In the negative in front of the 1/2, that told me the quadrants. I know where the terminal arms will end, but what about the 1/2? That tells me what the reference angle will be. But where does tangent equal 1/2? The tangent of what equals 1/2? Well, that is not something we can figure out from a special angle or from a special triangle. So for this, we need a calculator. And so at this point, we need to go to a calculator, like I said. And so how do we use our calculator? Oops, so I can spell again. Need a calculator. Well, as usual, I don't really care about the negative anymore. All I care about is the 1/2. Where does tangent equal 1/2? So I go to my calculator and type in the inverse tan of 1/2. Again, the negative part told me which quadrants my terminal arm would be in. I knew that right away, so I don't really care about that. So I'm going to type in the inverse tan of 1/2. And my calculator tells me approximately 27 degrees. And so that is my reference angle. It's not one of my answers, because that's where tangent equals 1/2. But who cares? It's my reference angle, and that's really what I need. And so now that I know my reference angle is 27 degrees, I know this is 27 degrees about. I know this is 27 degrees about. And so now I know how to figure out this angle from here to here. That's going to be the same as 180 minus 27. Which is 153 degrees. And this angle right here, which is going to be the same as 360 minus 27. It's almost all the way around. And 360 minus 27 is 333 degrees. Now these are actually both approximations. So I'll put a little dot over my equal sign. Because again, if you go to your calculator, the inverse tan of 1/2 is not exactly 27. It rounds to 27. There we go. So by needing a calculator, all that really tells me is that, or another way of looking at it is, if you don't need a calculator, your answer will always be a multiple of 30 or 45 or 60 degrees or something. If you do need a calculator, your answer is not a multiple of 30 or 45 or 60. And again, angles like 30, 45, and 60 or multiples of them are just nice angles to deal with. Hence, we call them special angles. And so this last one, where does sine of theta equal negative 0.8090? Well, I don't know, but I do know where sine is going to be a negative value. Sine is negative somewhere in this quadrant and somewhere in this quadrant. That's where sine is negative. And like before, I don't know yet what the reference angle is, but whatever it is, it's the same in both. And so now my task is to figure out that reference angle. And again, I clearly am not going to expect you to memorize where sine equals 0.8090. So again, I need a calculator for this question. And so again, I go to my inverse sine function. And I'll type in just the positive 0.8090. It's not wrong to type the negative in, but there's a good chance the answer that comes out will be more confusing for you. Again, the negative matters just for me to figure out in which quadrants my rotations will end. But after that, I don't care about it anymore. So I'll just type this in. Again, I know where my rotation is going to end. And so I'll go to my calculator, and I get something pretty close to 54 degrees. And so again, 54 degrees is my reference angle. And so now I can piece everything together, because each of these angles here is about 54 degrees. And so that means this first angle from here to here is going to be 180 plus 50. Or sorry, plus 54, which is about 234 degrees. And this angle here is going to be 360 minus 54, just shy of going all the way around, which is 306 degrees. And so I'm solving equations. I'm finding the value, or values actually in these examples, of a variable. But the variables are inside a trigonometric function, whether it's a sine, tangent, or cosine. And some of these we didn't need a calculator. If we don't need a calculator, we can go back to our special triangles or our special angles. But if our reference angles are not a multiple, or if our reference angle is not 30, 45, or 60 or something like that, then we will need a calculator. But that's not a big deal either. All right, so again, very abstract. It's hard for me to say this is inherently harder than what we were doing before. There's less calculations than what we're doing with like the cosine law, but it is definitely more abstract. It's easier to visualize a triangle and find the length of a missing side in a triangle. You can see it, you can draw it. We're talking about rotations here and the sign of a rotation. I understand if it's, abstract. But this completes this part of the trigonometry unit.